Hi, welcome back to Probabilistic Programming 1. We've done model specification, we've done parameter estimation, and now we're going to do model evaluation. So we have our model. It consists of a prior distribution and a likelihood function. Those are choices that we made. We could have made other choices. And we now have some belief over what this value, of what the most probable value for the rate parameter theta is. Suppose you meet someone who has a different model. They are absolutely sure that people cannot tell the difference. So they say theta is 0.5. And can you say something about the probability of this person's belief given the experiment that you performed? So technically what you're doing is you're comparing models. This person has a model, you have a model, and model comparison in statistical literature is known as hypothesis testing. So you start with a null hypothesis. In this case, that's the other person's belief that theta is equal to 0.5. And then we have an alternative hypothesis, namely that this person's belief is wrong, that theta is not equal to 0.5. So if you would like to compare models, within the Bayesian perspective, this just boils down to the same application of Bayes' rule. We have a prior belief over hypotheses, we have a likelihood of an hypothesis, and then we have a posterior belief over hypotheses. But now, because you're comparing models, you're not looking at the probability of a single model, you're looking at the probability of a model relative to another model. That means that you're taking ratios of models. That's what we describe here. So we have the posterior belief over hypothesis 1 given the data divided by the posterior belief over hypothesis 0 given the data, and that consists of the ratio of prior beliefs times the ratio of likelihoods. Note that the evidence term P of D, that is missing. That's because we're taking the ratio and because P of D is the same for both models, and therefore it cancels out. So usually we can't compute the evidence term P of D, but it's now implicit in this relative model comparison. So the most important thing in this equation is to compute this ratio of likelihoods, which can be quite hard to compute in general. There are special cases where you can perform some simplification to that ratio, and this just happens to be one of those special cases. In this case, we have a very specific value for the null hypothesis, namely theta is 0.5, and the alternative hypothesis is that theta is not that value, 0.5. So then this ratio of likelihoods, which is also called the Bayes factor, reduces to what's known as a Savage-Dickey ratio. And I encourage you to look at this reference, the appendix of this reference, to get a bit more information on the derivation of the Savage-Dickey ratio. I'm not going to do that here. That'll take too long. In that case, the ratio of likelihoods simplifies to the probability that theta equals 0.5 under your prior, and divided by the probability that theta equals 0.5 under your posterior. So if we compute that, that tells us that, so these are known, the prior and the posterior that we defined in the earlier parts of this notebook. That tells us that the statement people can discriminate alcoholic from non-alcoholic beer is about 200 times or more than 200 times more probable than the null hypothesis that people cannot discriminate alcoholic from non-alcoholic beer. Alright, that concludes Probabilistic Programming 1. A small statement before we move on to Probabilistic Programming 2. After each Probabilistic Programming session, I will make an assignment available on Canvas. You can download the assignment there. It's a notebook. I want you to enter code in that notebook. There are cells that assert whether that check whether whether your answer is in the correct format. They don't check whether your answer is correct yet. So once you've completed the notebook, upload it back onto Canvas. I will then download it, run an autograder, and give you back your score. These assignments do not count towards your final grade. They will only count if your if your final grade is between a 5 and a 5.5, and then just like your Piazza contribution score can give you bonus points, your probabilistic programming assignment participation can also help you pass the bar. So good luck on that. If you have any questions on the assignments, just post them on the Piazza forum. And I will see you in probabilistic programming 2.